Okay, welcome everybody to this little tutorial on exchange correlation potentials. You know, in DFT, in density functional theory, we have hundreds of them, and in the next 20 minutes I cannot explain you everything about them and where to use them, but I want to give you some short overview of what is in these different exchange correlation potentials, and some ideas how they are developed so that you can judge what you're actually using here every day. And therefore we first look a little bit more basic theories to grasp concepts like what is self-interaction, and we will look at this in context of the Hartree approximation, and then we will see what is exchange. This is naturally occurring in the HARTREE-FOCK approximation, and then we look in density functional theory how these things look there. And first we focus on the local density approximation, discuss the concept of the exchange correlation hole to explain also the success of the LDA, and then we look a little bit beyond LDA, simple gradient expansions, GGAs, and some simple applications. In all these theories, of course, we want in the end to solve a many-body Schrödinger equation. And in the quantum chemical world, there are some simple approximations for that. For example, the Hartree approximation, where you make this product ansatz for the many-body wave function. Then there is the Hartree-FOCK method, where you use a determinant ansatz to incorporate the Pauli principle, and you can also make linear combinations of determinants and configuration interaction methods, and of course many things beyond that which are not so relevant for us here. Now let's first look at this Hartree approximation, and now I write the many-body Schrödinger equation into some local term, this HI here, and the electron-electron interaction term. And now if I insert my wave function, my product wave function, and then immediately I arrive at a complicated system of coupled differential equations, which individually they look like a single particle Schrödinger equation here, but for every wave function here I have a different potential that arises from all the electrons except the one electron that I actually want to describe. And this makes the Hartree approximation actually rather complicated. And therefore, what Hartree suggested is to average now over all particles. You approximate this potential in this way, so you make it particle independent, and with this so-called Hartree potential, you then come to the Hartree equation, which looks like a KOHN equation without exchange correlation potential here. So that means what has to be included in the exchange correlation potential is, one thing that has to be included is the self-interaction here, which subtracts the interaction of the particle with its own density. If we go one step further to the Hartree-FOCK approximation, then we use now a determinant wave function which incorporates the fermionic statistics in the way that if you exchange now in such a determinant wave functions to particles, and then the wave function acquires a minus sign, as it should be for a fermion. And yeah, with this more complicated ansatz, you arrive after some math at the so-called Hartree-FOCK equation, which now includes not only the spatial coordinate r, but also the spin sigma here. And we have now an equation that looks like the Hartree equation in the first part. And the second part, this is the so-called exchange term, which is a little bit more complicated and again depends on all the other orbitals and other spins. And this term actually describes the antisymmetry and the Coulomb interaction of the particle. Now, if we compare this to our Hartree equation, now with this self-interaction correction that we had before, and then we see that Hartree and Hartree-Fock look rather similar. Only thing is that we have the second term here only for the orbitals with the other spin here, and this makes the essence of this exchange principle. Now we can rewrite this last term here also in the form of a non-local potential, and then we see the Hartree-Fock equation has now this direct term and this exchange term where these indices I and j are exchanged here, and this is the origin of the name exchange in Hartree-Fock. Now you can interpret this, as I told you, as a potential which depends now not on a single spatial coordinate but on two spatial coordinates, r and r prime, as a non-local potential, and you can think that this is created by a density, again a non-local density, given by this expression here. And this so-called exchange density has some known properties. For example, if you integrate it, then you see that the contained charge is exactly -1. So this is how this hole here would look like. And in the limit of r prime goes to r, and then you come to this self-interaction-like form that we had originally. So this was all known already in the 50s here. So exchange was well understood, and everything that is now beyond is what we call nowadays the correlation, and appears now in the more complicated kinetic energy terms in our equation. So if we take now this know-how and transfer it to density functional theory, let me shortly remind you about the basics of the HOHENBERG, KOHN and KOHN and SHAM theory. Then we see we have again very similar expressions. We have the interaction with an external potential. We have this what we call Hartree energy before, and then we have all this unknown rest that in the KOHN-SHAM theory then was divided into the kinetic energy of the non-interacting particles and the exchange correlation energy here. And the derivative of this exchange correlation energy then actually gives this exchange correlation potential, which appears in the KOHN-SHAM equation. Now, that means if we compare now the KOHN-SHAM equation with the exchange correlation potential to Hartree-Fock or Hartree, then this exchange correlation potential, as we discussed already, corresponds either to this self-interaction correction here or this exchange term in the Hartree-Fock approximation. Now you can do a local approximation. You say I want a local theory, and Slater did this already before the invention of DFT, and then you arrive at an expression that says that this exchange potential here is some prefactors times the density to the power 1/3. And this was actually used in the early days of density functional theory quite successfully, with a little bit scaling sometimes, to make simple local density exchange correlation potentials. If you want to know why this was actually so successful, then it is interesting to look again at this exchange correlation density. I discussed already the exchange density, but you can extend this concept to an exchange correlation density, of course, and you can separate it into some local contribution and something that comes from the correlation function G here. The so-called Hole function is then multiplied to the local density, and you know that the exchange correlation energy is then given by a double integral over this exchange density here. In the local approximation, and then this means that this Hole function that we introduced here depends now not on two spatial coordinates, but only on the relative distance between them and the local density at a certain point. And one can now look how this looks in a system where the exact whole exchange densities are known, and compare them to the local density approximations. And you can see for the nitrogen atom here, so the exact exchange density, now we take a certain point here and look along a line for the second coordinate, and this is then at some other point. You see that the exact shape and the local density shape is actually very different. So you wouldn't expect a good performance for this, but if you compare now at the same point the spherical averages around this point, now for the exact and for the local density approximation, then you see there's actually quite good correspondence in these two different positions here, and the fact that this is not so sensitive to the real form, but just to this averaged form here, actually makes the LDA quite good in practice. So people now, of course, they tried to go beyond this local density approximation by making gradient expansions, which is a natural attempt already quite early. There were the so-called gradient expansions that were constructed, and for this you say, okay, my exact exchange correlation energy is this LDA exchange correlation energy plus something that depends on the gradient or on the square of the gradient, and the density is then given by a constant density plus some perturbation in the vicinity, this delta n here. So, and then we try to expand in terms of this variation of the density. Now there are certain things that we know. For example, the integral over the density has to be constant, therefore the integral over the variations has to vanish. So in this expansion of the exchange correlation energy, all the first order terms in the end vanish, and only the second order terms survive here. And for the second order terms here we can look, but do we know? And this second variational derivative here, which is called the exchange correlation kernel. Now in the homogeneous electron gas approximation depends only on the difference of r minus r prime. This is a little bit like what I explained to you before with the exchange correlation hole, the same property. And now you can look at the local approximation and go from real space to reciprocal space, and then you get in the local approximation a known form of this exchange correlation kernel for k equal 0 and a given density. Now, since you know this, you can use this as a starting point now to expand for different reciprocal lattice vectors, and you get an expansion of this kernel here with expansion coefficients alpha and beta, which belong then to the square and to the fourth order of the wave vector, and of course they also depend on the local density n0. Now, for the exchange correlation energy, this means that we get then expansion terms with this alpha factor and with this beta factor and with this gradient squares and squares of the gradient square and so on. It turned out that this is actually quite good for small r minus r prime differences, but performs considerably worse if you go in the limit of large r minus r primes. So that in overall, this gradient expansion approximations performed rather badly. So what people try to do next is to say, now don't make a strict expansion in the order of these density variations here, but rather I choose now a function that depends on the density, the gradient of the density, and the Laplacian, so that some exact properties that I know that they are fulfilled, or I try to fit this function so to reproduce exchange correlation energies of known systems. And of course, what you ideally want is that this approximation that you get then is non-empirical, is based on quantum mechanical principles. That is universal, so it is good for all systems. It should also be rather simple and in the end rather accurate. And now there are many forms of GGAs that are around. PBE is a very popular one, PV91 and so on, and that fall into these categories here. And let me just show you a little bit the difference between LDA and GGA in the end, and two examples. The first one is iron, which was one of the big improvements that GGA made over LDA. So in LDA, these are these dashed lines here. The ground state was predicted to be FCC of iron and paramagnetic, but we all know that iron is ferromagnetic and BCC, and this was higher in energy. And if we compare this to the GGA result, then we see in GGA BCC was the ground state, and the FCC phases were actually higher. And also the ground state volume was quite close to the experimental ones. So in this case, clearly GGA gives the better structure. And this is also true for chromium, but in chromium we observe that, for example, the magnetic properties are not so well reproduced. We find the equilibrium volume here, actually quite close to the experimental one. We see that GGA predicts chromium to be antiferromagnetic. This is also okay. In LDA, chromium was non-magnetic with a too small volume here. Now if we look at the magnetic moment of chromium, this is 1.2 here in GGA, which is almost a factor 2 too high as compared to the experimental one, which is 0.6. And as it turns out, if you take the GGA optimized volume and use an LDA to describe the magnetic properties, you get a quite good agreement between the theory and the experimental values. But of course this in the end always requires some testing what you actually then use for your calculation in the end. Now, of course the developments didn't stop here with the gradients. People added more and more to the exchange correlation potentials. In the meta-GGA, the kinetic energy density was added here as additional input to the functional. Hyper-GGAs were constructed where exact exchange energy, HARTREE-FOCK-like, was added. And then you come already to orbital-based DFT, which is of course sounds a little bit strange, but yeah, this is what in the moment gives sort of say best ab initio results. Also the costs were rather high. But this development here, sometimes called the Jacob's ladder to chemical accuracy, so things get better and better the more input you give into your exchange correlation potential. Now, yeah, with this I want to come to an end. I hope I could show you a little bit how these functionals are constructed, how they evolved out of local HARTREE-FOCK type forms with always increasingly more accuracy. Some know-how came from quantum Monte Carlo data, fitting to databases, and inclusion of all kinds of things beyond the density. In the end, you have to choose the correct exchange correlation potential according to the problem that you want to solve, the accuracy that you need. And yeah, I wish you good luck in this choice and thank you for your attention.